the 5G deployment and usage. So what are our key innovative and differentiating aspects? Well, the first of all is that we implement the O-RAN split.2, and we have already incorporated in our radio unit the fronthaul interface over XGS-PON. That means that we already, our radio unit, it's plug and play on a PON that supports XGS-PON. We also support a 10 gigabit Ethernet interface, but as I said, our target, our main goal is the PON. So with this solution, we have the interface simplicity and the lower complexity of the radio unit. Our radio unit is implemented only by hardware components or programmable hardware. That means that there is no CPU attached on our radio unit, or not a large CPU, and the functions run on special dedicated hardware. So another aspect is what I have said before. We are interoperable with other manufacturers and vendors. Most of the vendors are already on the O-RAN initiative, and the ones that aren't there, I guess, sooner or later we'll have to join, because the O-RAN is gaining momentum, and sooner or later everybody has to be there. And what the other functions that compose the Cloud RAN, those are running on COTS servers, on virtualizing environments, on VNFs, and that's easily option or approach to scale the system, to distribute the system, and to keep the costs of the RAN low. And these are the main advantages. So the radio unit that we have developed is mainly on the framework of this project. It's an indoor small cell. We have on the roadmap an outdoor smart cell that is outside the scope of this project, but both of them, the main difference of them is the output power and the capacity to have external antennas and to be compliant with EMC and environment standards in the case of the outdoor. But the most important thing is that they are already compatible with XGS-PON, and they implement the split 7.2 from O-RAN. For the time being, we are supporting the N78 band, which is the most interesting band for the time being. But we are able to on future developments, we are considering the possibility to support other bands as well. In terms of channel bandwidth, we support up to 100 megahertz, which is also the ideal for these bands. So, and with these words, I will finish my part, and I will pass on to Professor Arnaldo Oliveira from the Institute of Telecommunications, which was our partner on the development of this radio unit. Arnaldo?
Okay, thank you, Peter. I will share my screen. Can you see my slideshow?
Yes.
Okay, yeah. Thank you. So I will give you a few words. First of all, good afternoon, everyone. Thank you for your attention. I will give you a few words about the designing of a 5G RU from concept to prototype. Vitor already provided the key concepts, the key motivation. So, and our target was to develop a laboratory prototype of 5G RU. So the initial target was to create something that is compatible with our RAN split 7.2, but the basic architecture, the components selected should also be compatible or provide the path to create later other functional splits between the RU and DU. So the target was also to support FR1 band up to 100 megahertz of channel bandwidth and up to 4x4 MIMO. With these requirements, so being flexible, being upgradable, we decided to create an FPGA-based or a MPSoC or multiprocessor system on chip based implementation, which means that architecture can be either upgradable in field or when it is ordered by a particular customer. It is based on software-defined radio approach because we want to have some agility in terms of radio processing and supported bands. It provides optical interfaces as well as electrical interfaces for fronthaul. And as already Vitor mentioned, several scenarios must be supported, either outdoor and indoor, which means that in terms of amplification stages, we must be flexible. So the amplification models are pluggable into the basic architecture, which means that flexible output power, and for some situations DPD is also important, which means that DPD will be supported for higher output powers. So this is the basic overall architecture of our prototype. So the target was to create a lab prototype based on development kits that allow us to parallelize different developments that must be done in scope of the project. I don't know if pointer options, yes, laser pointer, okay, great. So our main developments in scope of the project in our prototyping activities were based on this development kit that contains a multiprocessor programmable systems on chip from Xilinx. It has programmable logic, embedded processors, interfaces that allow us to, on one hand to connect to the optical fronthaul, on the other hand to the board that implements the software-defined radio front end. This base FPGA kit allows us to connect two of these front ends, which means that we can have up to 4 antenna elements connected to the baseband processing that is performed on the FPGA. We also developed 5G amplification chains for both, of course, uplink and downlink, containing amplifier, filters, and all the remaining components that are required to build an RF chain. In the scope of the project, we also developed 4G amplification chains, and since we have full control of the switches, duplexers, and so on, circulators, we can have flexible configurations in terms of standalone or non-standalone deployment. So this platform, in fact, provides both 4G, 5G capabilities for both standalone and non-standalone deployments. So going now into the what is inside the MPSoC, so what is inside the FPGA. Here is the basic architecture, is what is expected from the 7.2 split, functional split. So on one side we have the Ethernet PHY that established connection to the optical fronthaul. Then we have the RAN interface, followed by some compression and decompression IQ blocks that allow us to save some fronthaul bandwidth. We have the blocks that provide the lower physical layer processing, so the baseband processing for the file low. And after that, we have at the end the digital up and down converters that establishes the interface with the integrated RF front end. So we have both the uplink and downlink the chains, and they are very symmetric. So they implement the dual processing for the uplink and the downlink chains. Here is the picture of our lab prototype. So we have the basic processing kit, the RF front end, that for testing purpose at beginning we used a DU emulator from Keysight. So we have here our, I would say, small fronthaul, and what we are evaluating here is the signal generation. So we are transmitting a 5G signal that is being evaluated by the vector signal analyzer. So that was the initial the validation of our prototype. So what is current status and further status? Because in fact this project is just a starting point in the development of a 5G radio unit. So the interoperability tests of our RU prototype are being successful. We are performing tests with different DU emulators, commercial DUs. We are performing also some RF signal integrity measurements. Recently, we started with Altice Labs the migration to to a RFSoC device. So while an MPSoC contains programmable logic, processors, and digital interfaces, an RFSoC contains everything that is inside an MPSoC, and as well as high-speed DACs and ADCs, which means that we can avoid completely the external RF front end. So we are able to integrate into a single device all the baseband processing or RAN interface, as well as radio frequency chains. Only amplification and filtering chains, amplification components and filtering components needs to be placed external the RFSoC. Our initial tests were based on the MIME 2x2, and we are now upgrading to MIME 4x4. Our baseband modem also needs to be upgraded in order to support other bandwidths below 100 megahertz, because 1 megahertz was supported from the beginning, other numerologies. So we are enriching our baseband model in order to extend capabilities of 5G physical layer. And since it is important for higher output powers, we are also integrating the digital predistortion and crest factor reduction models, because it is important to increase the efficiency of the overall system. So, and that's a very brief summary of what is our laboratory prototype that now is being used by Altice in order to create a real product. So thank you for your attention.
Thank you, Arnaldo. I will ask now Professor Paulo Monteiro to talk about the usage of the PON as fronthaul.
Okay. Good afternoon. Can you see my presentation?
Yes, Paul.
Okay, so what we've been studying here in MPPS1, so we have been studying how to transport all the signals to the antennas from DU to RU, and for sure the PON structure, passive optical network, is it's very suitable architecture for the fronthaul. For CRAN applications. Why? Because it also benefits from the inherently centralized control. So one of our works has been studying how transport by rate over Ethernet over PON. Anyway, you should be careful to accomplish with 3GPP. So, and also idea is also supporting not only the RUs, but also to support data service. So our idea is to support both mobile and data service. Since you have already a lot of installed fiber to the home, why you not use it for both applications? And also the idea is to reduce the cost. Okay, but as Vito already said, you should guarantee a maximum upstream delay below 250 microseconds. So this is one of the requirements from 3GPP. And also idea also is to guarantee the maximum throughput for data service. So this is one schematic, simplified schematic of a passive optical network. So where we have the OLTs, let's see if you can put here the pointer. Okay, so we have here the optical line terminal from the central office, and from the clients, we have the optical network units. Today, in the most recent next generation PONs, we are using TDM PON, and also we are using also wavelength. So we are using TDM PON in every wavelength. And for sure, in the part of upstream, so we need dynamic bandwidth allocation algorithms in order to giving us take into account the latency of the systems, and also in order to be fairness in terms of data transmission. So we've been studying different dynamic bandwidth allocation algorithms, and this is one example of one scenario that we've been working. This is using the function split option 7.1. We are considering for 5G 100 megahertz bandwidth, MIME 4x4. In this case, in this scenario, we are considering 8 ONUs, but in these 8, 2 of them transport mobile signals. So, and one of these ONUs can feed one sector, antenna with one sector, and other ONU can feed one array of antennas with 3 sectors. And these are considering the next generation PONs with the 2 bonded wavelengths, which gives approximately 50 gigabit per second. And also we are considering 2 distance from ONU to OLT, one with a distance of 5 kilometers, another one with a distance of 20 kilometers. And from here you can see the upstream delay. So this is C, it's conventional, and this is the version 1 and version 2. So 2 versions of dynamic bandwidth allocation algorithms that have been working. And we can see for the 5 kilometers and also for 20 kilometers, for sure for 20 kilometers, you have higher latency, you have higher delay. But we can see by using our algorithms that we develop in framework of 5G, we can have a lower latency compared with the conventional dynamic bandwidth allocation. From here, you can see also the data service from all 8 ONUs. And you can compare here also from the conventional DBA, and also with our version V1 and V2. And you can see for sure we have higher fairness and higher bit rate using these new dynamic bandwidth allocation algorithms. This is one of the topics that have been working. We also make the first preliminary experimental results where we're using from Altice, the NG-PON2. And in this case, we use open air interface, and we are optimistic in terms of the results that we got up to now. But also we are looking more, and this is one example for looking for more advanced fronthauls And this is one example, experimental results, where we are transporting 5G fronthaul, but with coexistence with end-to-end 4G networks in real time. So in this case, we have two 4G networks, one using split 8 and the other one using split 7.1, where we transport, and this is the user equipment, where you can receive high definition videos. And also we have in this fronthaul also transport of 5G, 100 megahertz of bandwidth, and so using 8 kilometers of standard mode fiber, but also we include free space optics. Okay, in some scenarios it can be very important for free space optics, and also you show the reliability of this system in terms of the time, so the robustness in terms of the time, and we can see that it's possible to transport with low AVM, and we can get, and this is the power, for sure, since you are using a free space optics, it's not so stable like using optical fiber, but you can see a very good robustness of the system, and also you can show here the 64 QAM. So this is what we've been working in Mobilizador 5G, and also this is our with more details we can from this publication from Journal Optical Communication Networks, and also in framework of the project we have also been published several papers, and if you need more information, please let me know. And this is what I want to show you very briefly what we have been working in terms of fronthaul.
Okay, thank you, Paulo. We will now move on to the next presentation from Ricardo Leitão from Wavecom, and he will be speaking about 5G probe that was developed on this project. So, Ricardo, when you are ready, you may start.
Hi, everyone. Are you seeing my presentation?
Yes.
Okay. So I will talk about the 5G probe that we developed in this project. I will try to be brief. So the main objective of this probe was of this system to probing the 5G network was to create a series of probes that will collect different metrics, especially spectrum of the 5G signals, and send those signals to the centralized service. So the main motivation for this probing is to monitoring the new type of service that 5G can provide us, since we can have now different requirements for availability. For example, for critical communications, it's important to guarantee that we have 5G signal available. So that's one of the main motivations. Another one is about the spectrum used. I think for the first time, at least in Europe, we are using frequencies between 3.4 and 3.8 gigahertz. So at least in Portugal, maybe the numbers are a little bit different in other countries, but at least in Portugal, those are the main frequencies. And with those higher frequencies, we have a different kind of coverage. So if we mix together these two types of motivation, and we see that with the critical communications and a different kind of propagation, we might have a few problems in coverage all the area with the 5G. So this probe has the main objective of collecting spectrum information. As I said, this information is mostly based on channel power, identification, identify occupied bandwidth, and using the spectrum, identify if there is any kind of interference that can degrade the signal, and then the experience. Trying to change. Okay, so if we imagine a 5G network with all the elements that can generate traffic, we can have trains, bus, users with smartphones, and for example drones with the 5G connectivity. We can place different probes in that network that will be probing the spectrum in a passive way, so without any kind of connection to the 5G network, and they will collect the spectrum, analyze it, and send it to a centralized service. In that service, the information will be stored, and the information can be manipulated and be used to identify any kind of problems, and, for example, set alarms for example, for operators to identify problems in the network. Looking at the architecture developed for the probe, this is a modular approach. So we have a main block that's a controller that will control all the elements that the probe has, and will give an interface to a centralized service. It can be compatible with the different kinds of centralized service. And the second block, it's the data aggregation. Like the name says, it aggregates all the data that can be collected, all the metrics that we can collect from the network, and sends to the centralized service. So for this project, we are mostly using 3 blocks, one for coordinates, the spectrum capture, and one for power estimation. This block can be used also in the centralized service, and it's somehow optional. But since it's a modular approach, and we are looking to keep adding new features in the future, we are also working with other blocks and in another project to add more functionality and keep evolving this probing. So the main use case in this project is, like I said, spectrum and power analyzer. Like I said before, we can identify channels that we want to monitor and define, for example, a certain threshold to identify if it's something wrong, if the channel goes below a given power. You can set an alarm when that happens, and the centralized service, it's the place where all the information needs to be stored, and will provide a history of everything that happens. Another use case, and this was a challenge that was given to us in the middle of the project. We didn't cover initially this kind of coverage, but we adapted our modular architecture to create a 5G coverage of Aveiro. This network it has 3 base stations in Aveiro, so we we create, on the left, we create an interface. This was a local interface with a laptop and connected to the probe, and we were monitoring in real time the 5G spectrum and creating the map on the right to give a little more information about the coverage. This network was and it still is transmitting in the 3.6 gigahertz. So that's another way to use these probes. Instead of being stationary and always located in the same position, we can use them as a mobile probe to make a map coverage of a 5G network. So what's the next steps? One of those steps, like I said, was mobility tests. We are trying to add more features. One of those features is decoding LTE signals. This feature is in the almost ready for testing. It's in an advanced state, and after that implementation, we'll be focusing on the 5G decoding to add more metrics to the probe. Another approach that we are also looking is other technologies. Wavecom has already a lot of experience in TDT monitoring with Anacom, so we might add this approach to this solution. We are also looking to Tetra and VHF. Another point of interest is machine learning. This will be one of the main focus of a project that we will start very soon, and will be somehow a way to add more information based on machine learning and data science. So with this, I finish my presentation. Thank you all for coming.
Thank you, Ricardo. Let's open now the question and answers. I will ask you to ask questions. Podem fazer as perguntas em português também. Podemos comentar agora para português para esta componente de questões e respostas. Portanto, temos agora aqui período para quem quiser. Portanto, quem estiver interessado em fazer questões, por favor, abra o micro e faça a questão. Não há ninguém que queira fazer questões neste momento. Se calhar, então, uma vez que estamos um pouco atrasados, avançamos e podemos deixar a parte das questões para o próximo intervalo. Portanto, se quiserem fazer... Sim?
Eu só sugiro, sim, com isto ficamos na hora. E também sugiro que se quiserem colocar as questões por escrito no chat,
certo.
Depois também serão pegadas por nós e colocadas depois na próxima sessão de perguntas e respostas.
Certo.
Mas pronto, não se envergonhem, qualquer pergunta é válida. Portanto, ou façam na próxima sessão de perguntas e respostas às 15h55 ou coloquem no chat que depois um de nós irá lê-las e colocar ao orador que não responderem.
Pronto, sendo assim, eu passava à próxima apresentação e recuperávamos aqui o horário. É o Bruno Antunes, da Wavecom, que vai falar sobre o CPE 5G, que foi desenvolvido no âmbito deste projeto também.
Can you see my slides?
Yes, Bruno, you may move.
Yes? Okay,
Yeah.
thank you. Good afternoon to you all, and also thank you for being present. Alongside the probe that Ricardo presented before me, Wavecom was also responsible for the development of CPE, CPE for, like the project, 5G communication.
Bruno, you are muted.
Yes, it unmuted the space bar. I use the space bar to change slides. So our first model in 2013 was mainly targeted at microwave links. It was the first model that Wavecom used, presented as its own brand.
Estás muted outra vez, não?
I don't understand why. I must use the mouse. Okay, thank you. In 2016, Wavecom presented the second generation that supported 3G and 4G communication. But this was an evolution from the previous model, the 2013 model. And in 2021, Wavecom will present the 5G capability model, or the modem with the model with 5G connectivity. So in terms of the motivation and goals for this kind of equipment, our main targets are the scenarios where we need multiple wireless or wired interface with different frequencies and technologies, mainly for the scenarios of machine-to-machine, IoT, critical applications. There's a demand for a modular component that can provide flexible radio solutions, and also a higher integration and support for new technology. The motivation also comes from our earlier models and the evolution from the earlier models, and the differentiating factors that we consider are the flexibility of this equipment, the fact that it can combine multiple wired and wireless interfaces in one box. Also the resilience, we can provide redundant communications on top of these multiple interfaces, and also a centralized management where we can monitor, manage, and also operate multiple units from a public cloud or a public or a private cloud, where the user can also orchestrate several units from one point. In terms of targets and align with the project, and also with some of the 5G use cases, and also with Avecom goals, our main targets are the industry and utilities, and also the transportation. These are markets where Wavecom is currently implementing their products, and we think that also are some of the main targets for the 5G networks. In terms of applications, for example, for the scenarios of smart cities, we can think of these as the IoT gateway, where we can combine several technologies. So we can combine the 5G technology with LoRa, LoRaWAN, Zigbee, Bluetooth Low Energy. So we can combine multiple technologies in one box, in one component. Also provide, for example, Wi-Fi connectivities in cities or in small areas. Support for CCTV communications. The scenario of building to building or pole to pole connectivity, where we can have a backhaul in microwave links, and then provide, for example, 5G connectivity in a small cell. Also for the transportation, a market where Wavecom is currently already it's already providing their models for 4G and 3G communications. We envision these as to provide Wi-Fi connectivity for passengers, for example, support of newer technologies, 802.11ax, for example, And also the fact that since we can support for multiple interfaces in multiple cellular technologies, we can have redundancy for the cellular connection. Also, as mentioned before, the possibility of having a centralized management to manage, to control the several units. Also, in general, all the applications that required connectivity or edge functionality. In the scenario of utilities, we envision this as the cellular router for utilities, where we can provide, for example, broadband private networks. Where we intend to support for private telecommunications, also critical communications, SCADA, security, link redundancy, where we can provide more than one connection to the site, and also Industry 4.0 compliance. Some data that we gather along the project, we were able to obtain almost 1 gigabit of throughput. We were able to measure an average of 826 megabits per second with peaks of 1 gigabit per second. In terms of a latency, and here bear in mind that this is end-to-end latency. We know that 5G is intended to provide 1 millisecond latency to the, but it's only in the radio unit. So we have what we are measuring here is end-to-end latency, and we're able to achieve 8.1 milliseconds of minimum value, and with an average of 15.9 milliseconds of end-to-end latency. I remind you. Also, in collaboration with INESC, the 5G CPE was also used as a gateway to provide Wi-Fi connectivity to what we consider the scenario of the first responders use case, where we provide Wi-Fi connectivity to a flying gateway. This will be explained in more detail after this presentation by INESC. And from our side, it's the brief presentation of the 5G CPE. Thank you very much for your participation. And
okay, thank you.
Give it back to you.
Thank you, Bruno. So now we will go to this specific topic of the extension of the coverage by using drones. And just as a point, Bruno said, the end-to-end delay, it's actually round trip, so it's one way and the other.
Yes,
so,
you are correct.
So end-to-end is half of that.
It's
in average.
Exactly.
Okay, so I will ask now André to do his presentation. André, are you there?
Thank you. Can you see my screen?
Yes, please. You may know.
Okay. Thank you. Good afternoon, everyone. My name is André Coelho. I'm a PhD student in telecommunications and a researcher at INESC Tech, working on wireless networks, with a special focus on flight networks composed of drones. I'm going to show you our main results achieved in the 5Go project in this presentation, entitled 5G on Demand, Connecting People and Things Using Drones. So nowadays, the demand for always-on connectivity brings up significant challenges for the wireless telecom networks. These challenges are exacerbated in temporary crowded events, especially due to the heterogeneous services and applications used. In disaster management scenarios, the first responders demand reliable, mission-critical, personal and machine-type wireless communications. In outdoor festivities, marathons and rally car events, the spectators, the media and the staff may use rich media communications with the different quality of service requirements. The 5G technology represents a step forward to achieve the broadband and low latency networks in order to enable communications for high densities of mobile devices, ensure high bit rates under controlled delays, and enable the interaction between humans and machines. Okay, sorry. So, considering the evolution of wireless communications technologies over years, in addition to the new services and applications with stringent requirements that have emerged, the main objective pursued has been to ensure always-on connectivity anywhere and anytime. The main existing solutions to address this challenge rely on fixed base stations, whose location needs to be planned considering the maximum capacity demanded. This may lead to underused base stations when the amount of traffic exchanged is low, and capacity problems if the traffic exceeds the amount of traffic that was considered in the design. In addition, a problem that may appear is coverage issues if the base stations are damaged, as it was happened in Portugal in the forest fires in 2017. An alternative solution is based on mobile base stations mounted in vehicles, which is commonly known as the cells on wheel concept. However, they have important mobility and parking constraints. Their number is limited, and they are a non-cost effective solution. Unmanned aerial vehicles, also known as drones, have emerged as flexible platforms capable of operating anywhere, anytime. The ability of drones to move and position in the 3D space, their capability to hover above the ground, and their capacity to carry cargo on board make them suitable platforms to carry communications nodes. Within this context, flying networks composed of drones acting as Wi-Fi access points and cellular base stations are emerging as a solution to enable the on-demand and dynamic placement of communication cells in order to extend 5G coverage and capacity. The 5Go project proposes a drone acting as a flying access point for providing broadband internet access in temporary crowded events and mission-critical communications for first responders in disaster management scenarios. For that purpose, the flying access point placement is autonomously defined according to traffic demand and the positions of the ground users, enabling the agile establishment of 5G coverage and the enhancement of network capacity on demand. The flying access point forwards the traffic between the ground users and the internet by means of a wireless link established with a 5G customer premises equipment, such as the one developed by Wavecom. The CPE, which may be deployed in an emergency vehicle, acts as a gateway to the internet, taking advantage of the 5G technology as backhaul. Multiple flying access points can coexist and establish wireless links between themselves, forming a multi-op flying network able to further extend the 5G coverage. In this network, we take advantage of the mobility of the drones to define their optimal placement over time. In addition, taking advantage of the information on the future movement and placement defined for the drones, we ensure the optimal communications resource management by proactively defining the forwarding tables, computing the queue's size, and configuring the optimal transmission power to be used by the flying access points. The flying network is controlled by a node with a holistic knowledge about the network deployed on the edge. At Inestec, designed a set of algorithms which are relevant scientific contributions, traffic-aware placement algorithms, which allow to define the optimal positions and the transmission power of the flying access points, considering the traffic demand and the positions of the ground users. And the energy consumption of the drones was also considered in order to maximize their endurance and the availability of the network. In addition, we developed a proactive routing protocol, which computes in advance the forwarding tables of the flying access points and the time instance. They shall be updated in order to avoid wireless links disruptions, even when the drones are moving. And a proactive queue management algorithm, which computes the queue size of each flying access point in order to ensure controlled delays for the transported traffic. The experimental demonstration carried out consisted in extending the coverage and reinforcing the 5G capacity in order to provide communications to the user of a damaged car in an area without 5G coverage. For that purpose, the flying access point depicted in the figures was used, which is based on a rotor-ring UAV or drone that was developed at INESCTEC. I will now present a short unedited video of this demonstration that was carried out. This is an illustrative scenario where a drone provides wireless connectivity in an area without 5G coverage, where a foreign person traveling around our country needs to know the national emergency contacts. The user could then establish a video call in order to ask for help. In addition, the temporary wireless network provided by the drone may also be useful for the first responders, so that they can send photos and videos to the command center, establish reliable communications between themselves, and use personal devices for remote monitoring of their vital functions. With the objective of disseminating the results obtained and validate them among the scientific community, scientific publications in international high impact factor conferences and journals were pursued. This is a summary of the publications and dissemination activities achieved by INESCTEC in the 5GO project, which includes 8 papers, 1 MPSC thesis, 2 ongoing PhD theses, and 6 participations in international scientific conferences and workshops. At INESCTEC, we believe that our research in wireless networks is perfectly aligned with the emerging 6G paradigm, which is already being discussed in industry and academia. In order to achieve the ubiquitous internet connectivity, a vision that is part of the 6G is in fact the use of non-terrestrial components, such as drones. When it comes to potential technologies, it is expected that 6G will take advantage of the terahertz communications. This will enable wideband channels with tens of gigahertz bandwidth. The terahertz communications impose significant challenges since they rely on high precision between transmitters and receivers, and may benefit from the line of sight that is provided by flying networks. Artificial intelligence will also be a powerful tool to solve problems that are too complex to be solved in real time, and for which there is no heuristic algorithms and solutions to solve the problem now. So overall, the goal will be ensure efficient, reliable, and low-cost communications. These are also aspects that we are also working on at INESCTEC. So the growing usage of heterogeneous services and applications, including broadband internet access and mission-critical communications, and virtual and augmented reality, imposes always-on connectivity anywhere, anytime. Flying networks, composed of drones acting as flying access points, are emerging as a solution to extend and reinforce the 5G coverage and capacity, taking advantage of the ability provided by the drones to be placed in the 3D space. Actually, both academia and industry are already discussing the 6G paradigm, including requirements, research challenges, and potential technologies. So we believe that it is time now to think about 6G, and in fact at INESCTEC we are already doing it. Thank you.
Thank you, André. So we have some questions that we will save for the next question and answers period. So I will now pass the presentation to Rui Calais and Jorge Proença that will be talking about virtualizing the CPE.
Hello, good afternoon. I hope you're seeing my screen.
Yes, you may move on.
So we'll be talking a bit about the virtualized CPE. This may seem a little bit off topic since we have been always talking about 5G, and this VCPE we'll be talking about is you will be talking about the virtualization of the fixed network CPE. The link, the connection to 5G is that we are in fact using the same technologies and the same technology support on the edge of the network that is available for 5G. So what is this problem of the CPE? We consider here two kinds of CPEs. We consider the residential CPE, or the home gateway, which usually scales up to millions on the network, and is in fact a real operational headache for operators just to update or to upgrade the base of CPEs for an operator. It might take weeks and cost a whole lot of money. So it would be very interesting for operators to be able to have these functions manageable, eventually centralized, both to make the operation easier, but also to be able to make the CPEs simpler and obviously less expensive. On the other side, we have the business CPEs, which are usually feature-rich and which features may vary depending on the specificities of the businesses. With things like distributed services, VPN, for instance. And so these CPEs should be able to be very flexible, so I could run many kinds of services on them. So how do we evolve? So we go from a CPE that is an engineered system, basically, that is a box connected to a telco network, to a new scenario of a telco cloud, which involves the CPE. Of course, it will have to be there, but it may have the possibility to run virtualized functions. It may involve the edge data center, the edge of the network, and eventually data centers at the core of the network on a distributed and virtualized environment. So the CPE, these functions, the first step towards this is to be able to disaggregate these functions. They're all together on a CPE, so we'll have to be able to disaggregate them, identify them, and then virtualize them. Once we've done this disaggregation and virtualization, we'll be able to place them wherever they fit better, either at the CPE or at the edge of the network or at the core of the network. Of course, that being able to instantiate these functions wherever we want and whenever we want also means that we need to have a very, very flexible network so we can steer the traffic between these functions, and so we need a network that is SDN based, so we can in real time on the fly be able to change this network as we change the network functions and where they are at every moment. But if we by managing to do this, we can have functions that can be managed separately, that can appear whenever and wherever I want, and so we'll be able to tackle many of those problems that I have mentioned before, and also we'll be able to do something else that is very, very important, which is to deploy new services on the fly. Not only be able to manage the services that we have, but also to deploy new services on the fly and then create an environment for innovation, and also create business opportunities, because here we can, for instance, enable our customers, for instance, the residential customers, to subscribe to a service or to a function and have it deployed directly on the CPE or on the network or somewhere, and have him have access to that network that just wasn't there before. So the architecture for this is based on these three figures: the CPE, the physical CPE, which may or may not be able to run virtualized functions, the edge data center, and the core data center. Either on the edge data center or on the core data center, we'll have a CPE manager, which will be able to manage the life cycle of our virtualized functions, and work a little bit as a NFV orchestrator, as a mano for these functions, and be managed by a portal, which may be the portal of the operator for provisioning the CPEs and for creating new services and managing the whole life cycle of services and CPEs, but also the portal, the user portal, where you can subscribe to new functions. So in the end, what we will have for traffic is this ability to go through the functions that are defined, either passing them by. For instance, if this is a firewall, the traffic will pass by them. If this is a terminal function, like say DNS, it will be the terminal will land here, or some kind of server. So for this architecture, we have defined a prototype. What in the project, what you have produced here, besides the architecture, was a prototype for this, and this prototype is totally supported on the 5Go OpenStack platform. So it's completely virtualized, and I mean completely. I mean even the user equipment, the CPEs. The central office that supports the CPE manager, all are virtual machines. Then the functions, the network functions that we want to move around are Docker containers that will be running either on the CPE or on a cloud central office. On a collaboration with another sub-project of Mobilizer, of PPS2, we have also managed to coordinate to coordinate the VCPE with the business support and operation support system, or NAP, that is available. And so our Cloud Central Office CPEs, all this is at first deployed and bootstrapped by our NAP, which will then and then we'll interact with the VCPE manager to manage the services via the portals. these portals were also thought of in this project, namely the client portal, which we have just made some mock-ups of it. We've not actually developed a client portal, but we have prototyped a functional portal for the operator for the CSP, where we can deploy our services, where we can also do some operations that could be done on the client portal, like subscribing the service or activating it. And this is what Jorge Proença will be showing you now in a short demo video of the operation through this portal. Jorge, please go on.
Yes, so I will share. Okay, I think that you can see my video, and I will make I will show a video demo that will be divided into 3 main parts. The first part will be a brief video of the interaction between the ONAP orchestrator that is being used in the PPS2, that's being used to deploy the infrastructure that is supporting the VCPE manager. And using the ONAP portal, we can create and instantiate the services that will manage the clients, the users, and the virtualized CPEs. And then I will show the 2 examples that Rui mentioned of the small CPE that provides connectivity between the customer premises and then the Cloud Central Office, where the functions are only instantiated in the operator infrastructure. So using the ONAP portal, we will enter the VCPE dashboard and we will create a customer. And when this customer is configured, we will then create and associate a service to it. In this case, this is a high-speed internet access service. And to this service, we will make a provision of the CPE. And when we provision the CPE to a client, we can define the type of CPE, if it's a small or a large CPE, and this will define where the functions can be instantiated. In this case, the small, you can see that both the base functions that provide internet connectivity, which are the routing and the DHCP and DNS functions, they will be deployed at the central office. At the moment, they are pre-provisioned and they will be instantiated when we activate the VCPE. This can be done manually, as we are doing, or can be automatic when the VCPE is connected to the infrastructure. So at the moment, the VXLAN tunnels between the customer premises and the operator established, and also the containers that are running the functions are running. And if you go to a user equipment in the with this solution, the operator can easily manage the functions because they are located at its infrastructure, and it's done in the easier way compared with the traditional management of functions in the current CPEs. And now we are seeing the screen of a user equipment that has asked for a DHCP lease, and it now has an IP address, and we can do some connectivity tests. And now we are pinging one of the virtualized functions, in this case the vRouter. and then we will establish the connectivity to the internet. And this is going through the IP, the layer 2 tunnel between the two premises. And then at the CCO it's going to the internet. We can also have some web browsing experiences. And now we are going to show an additional subscription of a function, a network function that can provide ad filtering. Because in the standard service, we can see that the web browsing is showing some ads. Now we subscribe to a premium function that provides DNS-based ad filtering. And this is, since this is DNS-based filtering function, this will have some dependencies. And in this case, it will trigger a configuration change in the already in the main DNS functions. So that the queries will go, DNS queries will go through these premium functions, and based on a blacklist, they will be filtered when pointing to some ads. And as you can see, the web browsing experience doesn't have any ads, and there are some queries that were blocked. And now, in the second scenario, we will deploy a large CPE that can have some functions associated in the customer premises. So a mix of functions. Some are deployed in the cloud operator. As you can see here, the vRouter is being deployed at the CCO, and the DNS mask that provides the HTTP and DNS is being deployed remotely at the customer premises. And when we activate the CPE, you can see that the tunnels are established and the functions are deployed, the router is deployed at the center, and we can see that the DNS and the HTTP are deployed in the customer premises. And as in the first scenario, the client can get the IP address. In this time, the IP address is being done locally in the CPE, and it has connectivity between the services, to the vRouter, to the DNS service, and also to the internet. And so this concludes this video demo. Thank you.
Okay.
I just wanted to add, I forgot to say that these two scenarios that we shown, the small CPE and the large CPE scenario, mean to show that the architecture is quite transparent to the actual capabilities of the CPE. So if we have a smaller, less powerful CPE, we can deploy less functions or almost no functions there. And if we have a large CPE, it can support more functions, and we can deploy functions there.
Okay, thank you. We have some questions, and we have some of them that are addressed to you, Luis, so we can start from the end. So there is a specific question for you, Luis. What are the minimum requirements for the physical CPE at the customer premises?
Well, it has to do with what I was just saying. So the idea of this whole architecture is that we can deploy functions, and that we can deploy a rich CPE even when we don't have a very powerful CPE equipment. So if we have an equipment that is just able to communicate with the edge and there's almost no functions there, it should be a very inexpensive CPE, and then we can deploy the functions on the edge. If we have a somewhat stronger CPE with a powerful CPU that is able to run virtualized, to run cloud workloads, then we can make those functions run there. So the idea, we don't know what are the minimum requirements, but the idea here is that they should be as few as possible.
Yes, the base services requires that the physical device is capable of establishing a layer 2 tunnel, in this case a VXLAN tunnel, to the data center, and that it is able to forward packets. It's like a network hub. It's basically a network bridge.
Yes, you will just have a bridging device. Yes.
Okay,
there's all the functions on the edge.
Okay, there's another question to Jorge. Out of curiosity, which functions are you implementing on the Docker, and can the client customize functions using Docker containers?
Yeah, at this moment, we are implementing the basic functions, the vRouter that provides routing and firewall. And we also have another function that provides the HCP service and DNS service, and this is done using the DNS mask service. And we also have the ad killer, which is a keynote function that is done using the Pi-hole. The client customization, we did not develop the client portal, but the client is not aware that the functions are running on Docker containers. That is abstracted from the client.
Yes, we'll subscribe them always as some kind of a service.
At this time, we don't have the customer portal, but we can manage the functions. If we go directly to the functions, we have a web interface for individual functions. But as a whole, as the service, the client cannot configure it, just function by function. And in that case, it can configure some parts of the function configurations.
Okay, thank you to you all, to you two in particular. Now we have another question to André Coelho, which is, do the current available drones in the market have enough autonomy to make this a reality? André?
Yes, can you hear me?
Yes, go on.
Regarding the autonomy, yes, there are nowadays there are the research on, for instance, wireless power transfer in order to power the drones even when they are flying. In addition, they can be provided with solar energy, for instance, and also our algorithms also take into account the optimization of the movements of the drones. For instance, there are every drone has all the drones have an optimal speed for which their power consumption is minimal. So we are trying to include this optimization in our algorithms so that we can maximize the endurance of the drones and the availability of the flying network.
Do you have any reference value for the autonomy currently?
It depends. It depends on the payload of the drone. Minimum value, I would say half an hour, for instance. But for the payload, if the payload it depends on the payload. It can reach up to 2 hours, for instance, 3 hours. It depends on the payload that the drone is carrying.
Let me add that in this work line network edge we have worked with this development on the drones, but in the 5th webinar regarding the human-centric communications, another partner also developed work around drones and drones communications and drones applicable to several verticals, and that has to be answered. But one of the solutions for this is also to use fixed wind, asas.
Propellers.
Fixed winds drones, and those could last without any specific technology for several hours flying. So one of the drones developed in the project in that other scope of work is able to do that. So there are several ways of improving that. But please go to the 5th webinar and you'll get some more information about this.
Okay, now we have, sorry, continue.
Sorry, just to complement, in this type of networks, the drone does not need to be always hovering. We can also use the drones in order to place the communications nodes on demand, and then the drone can be on the platform, for instance, on the static platform, and we can use the drone just only when the traffic or the users are moving, so that we can replace the nodes on demand. But the drone in this type of network that does need to be always hovering.
Or could be flying in circles above the area.
Okay. Thank you. So now we have 2 questions for Bruno and Tunes. Well, there is a question about the values, if they are for standalone or non-standalone or both. I don't recall which values are these questions about. Maybe the round trip, I guess.
When Bruce was presenting the downlink and uplink speeds and latency.
Yes, I assume.
Can you hear me?
Yes, please.
Okay. So I think they refer to the slides of the throughput and the latency. Those values are for standalone mode. We were able to get around 400 megabits in non-standalone and the minimum value of latency of 10 milliseconds. Though we have to consider that in the non-standalone implementations, we were sharing the core with the other components of the network. So these values are for the standalone. Regarding the other question that was addressed, in terms of
slicing, yes.
Exactly, slicing, we weren't able to validate it in this project because the cores that we were using and the cores that were provided for testing didn't support slicing. Also, slicing, at least from some conversations that we had with other operators, in non-standalone, it will not be a priority, at least for the first implementations.
Okay, I don't know if there are any other questions to any of the presentations that were done during this afternoon. If not, you can always put those questions afterwards and we will try to reply by email, or we can have a special session one-to-one if you want to talk about any of the solutions with any of the partners that present them. I guess all of them are willing to do this talk if you want. And now I will pass on to Francisco Fontes that will be presenting a little bit of the next work, the next webinar.
Okay, so I think I have my micro open. Yes, I have. Okay, so we're about to conclude. So just presenting the next ones, but specifically the next webinar that will take place next Tuesday at the same time, focusing in the network core. So this is the overall agenda. So we'll address the 5G core. So what we have been doing specifically for components that integrate 5G core network. So components, virtualized components for the 5G core. And then management plane. So all this will be orchestrated, observed, must be secure. So we'll have a set of presentations in this scope. So all 5G components, even the access, is becoming virtualized. They need to be monitored with new strategies. Augmented artificial intelligence, machine learning is needed because of the increasing complexity of the network, and then also security. So the attack surface is much bigger now that everything is becoming a software, and because we have a more complex system with much more components. All the 5G architecture is based in microservices, so many components, even if they are stateless, but the attack surface is much bigger, so security plays a strong aspect that should be taken into consideration. So these are the first part, and then we'll conclude this with the demonstration of serious cases where everything is put together, also with results from other work lines, from the access and from the verticals, to show this. Just to provide you with a hint of what we have, what we'll be seeing, I'll show you a short slide video with that.
Welcome to the 5Go project. In this video, we offer an overview of the project results in the scope of the 5G core and complementary functions. The core section of the 5G networks comprises all the systems that support the delivery of 5G services. In the service plane, we have developed various security functions, such as an honeynet, which prevents and mitigates cyber attacks on virtualized functions, the VAS, whose role is to identify vulnerability and security threats. We have also designed two intrusion detection systems. The first is the app IDPS, which protects 5G core functions and their service-based architecture via smart pattern detection and policy enforcement. The second is a DNS IDPS, which protects the DNS service, one of the key services that underpins the internet by translating addresses like 5go.pt into IP format. We also developed EPVP, which collects and pre-processes security events, such as app IDPS, and presents them in a graphical real-time dashboard. And the AAA component, which provides an authentication, authorization, and accounting mechanism for 5G networks. In the management plane, we developed an assurance framework which ensures service quality levels for an optimal subscriber experience, the high-level policer that delivers the decision-making process in fully automated scenarios, and the 5G service orchestrator that orchestrates legacy and virtualized environments. Two very important functions were developed for the mobile core. The PCF, which through an autonomic manager adds intelligent mechanisms that govern various 5G network capabilities via policies, and NEF, which exposes 5G core services in a secure and scalable manner. Finally, we have three use cases that showcase all these systems in action. The VCDN service orchestration use case illustrates how, in a 5G network, a content server can be moved across the network to provide a better and smoother user experience. The public protection and disaster relief with the body kit use case is focused on IoT usage in 5G networks in the context of mission-critical communications. The goals are to optimize and configure resources, provide multi-vendor support and interoperability between different products, and assure the security of the 5G core components. The 5G service attack use case focuses on the resilience of a video-on-demand service supported by a 5G network. Once an attack is detected in the edge, the VCDN is migrated to a neighboring node, thus guaranteeing service reliability and performance. For more information on project results, please check out the project website and see our other videos on the project's YouTube channel.
Obrigado a todos. Penso que com isto concluímos a nossa sessão de hoje. So thank you all and keep in touch, and we hope to see you on the next webinar.
Antes de se ir embora, um pequeno pedido de atenção a um link que está no chat para um questionário relativo portanto, a esta sessão, que nos ajudará a todos a melhorar os eventos. Eu gostaria que pudessem responder, não demora mais do que 1 minuto. Obrigada, até ao próximo evento.